Look up on the clearest night of your life, and you will not see a single one of the most common stars in the galaxy. 3 out of every 4 stars in the Milky Way are red dwarfs, and not one is bright enough for the naked eye. In 1997, Laughlin and Fred Adams calculated that the smallest could burn for 10 trillion years, 700 times the current age of the universe. No red dwarf has ever expanded into a giant. None have collapsed, none have died. For decades, their dimness made them easy to overlook. Then, in 2018, the Gaia spacecraft revealed something unexpected in their structure. The most common stars in the cosmos have barely begun, and their story reaches to the last light the universe will ever produce. Today we trace their origin, uncover why they outlive everything, and ask what remains when only they are left. If you enjoy this, consider subscribing. The smallest stars carry the longest story. This is where it starts. There is a strange kind of invisibility that comes not from rarity, but from faintness. The night sky, on its clearest and most generous evenings, offers roughly 5,000 stars to the unaided human eye. Bright giants, distant supergiants, nearby yellow dwarfs like the sun, all of them burning with enough intensity to send their light across the void and into the back of a human retina. But the stars that dominate the galaxy by sheer number are not among them. Not one. The most common type of star in the Milky Way, the class that makes up approximately 3 out of every 4 fusing stars in the entire galaxy, is too dim to see without a telescope. Red dwarfs. Small, cool, and so profoundly faint that the brightest among them produces no more than 1/10 of the sun's light output. The dimmest manage barely a 10,000th. They are everywhere, and yet to the naked eye they do not exist. Consider the solar neighbourhood. Of the 60 nearest stars to the sun, 50 are red dwarfs. The closest star to our own solar system, Proxima Centauri, sitting just 4.25 light years away, is one of them. It is the nearest star in the sky, and you cannot see it. The second nearest stellar system, Barnard's star, is also a red dwarf. So is Wolf 359. So is Ross 128. The local cosmos is saturated with these objects, and if your only tool is the human eye, you would never know they were there. The numbers become extraordinary when you scale up. Research by Charles Larder at the Harvard-Smithsonian Center for Astrophysics has established that most stars in the Milky Way are not only red dwarfs, but single red dwarfs. Solitary objects drifting through the galaxy without companions. Their combined mass exceeds the combined mass of every larger, brighter star in the universe. They are not a footnote in the story of the cosmos. They are the main text, written in ink too faint for us to read without help. And yet, for most of the history of astronomy, they were treated as background noise. Too dim to study easily. Too small to produce the dramatic deaths, the supernovae, the neutron stars, the black holes, that capture attention and fill textbooks. A red dwarf does none of those things. It simply burns. Quietly, slowly, and for a length of time that makes the age of the universe look like an opening sentence. That is the paradox at the heart of this story. The most overlooked stars in the galaxy are also the most enduring objects in it. They were burning when the first galaxies assembled. They will still be burning when the sun is a cold, dark remnant, and the Milky Way has long since merged with Andromeda. They are, in every sense that matters, the patient backbone of the cosmos, and their lives have barely begun. To understand why, you have to understand what a red dwarf actually is. not as a category on a chart, but as a physical object. A ball of gas with specific properties, specific temperatures, and a specific internal architecture that makes it fundamentally different from a star like the Sun. A red dwarf is a main sequence star with a mass between roughly 0.08 and 0.6 times that of the Sun. The lower boundary matters. Below 0.08 solar masses, an object cannot sustain the fusion of hydrogen into helium in its core. It becomes a brown dwarf, sometimes called a failed star, an object that glows faintly from the heat of its own gravitational contraction, but never achieves true stellar ignition. A red dwarf sits just above that threshold. It is the smallest thing in the universe that can call itself a star. The surface temperatures are low by stellar standards. Where the Sun's photosphere blazes at approximately 5,700 Kelvin, a red dwarf ranges from about 2,000 to 3,500 Kelvin. This is cool enough for something remarkable to happen. At these temperatures, simple molecules can survive intact in the star's atmosphere. Compounds like titanium oxide, which would be ripped apart instantly in the searing outer layers of a hotter star. The presence of these molecules gives red dwarfs their distinctive spectral fingerprint and places them firmly in the M class of the stellar classification system, the coolest category on the main sequence. Their size is almost planetary. The smallest red dwarfs have radii just 9% of the Sun's, barely larger than Jupiter. If you placed one beside the Sun, it would look less like a companion and more like a leftover. And yet the difference between a red dwarf and a gas giant is absolute. One sustains nuclear fusion, the other does not. That boundary, 0.08 solar masses, the ignition line for hydrogen, is one of the sharpest divides in all of astrophysics. The luminosity follows from everything else. Low mass means low core pressure. Low core pressure means low core temperature. Low core temperature means a sluggish fusion rate, and a sluggish fusion rate means very little light. The largest red dwarfs, objects like Lacaille 8760 in the constellation Microscopium, manage roughly 10% of the Sun's luminosity. The smallest produce so little light that if you replaced the Sun with one, the Earth would be plunged into a darkness deeper than any night. If you could stand on a hypothetical rocky world orbiting one of these faint stars at the distance of Mercury, the star would hang in the sky no brighter than the full moon appears from Earth. A dim, rust-coloured disk. Warm enough to feel perhaps, but offering nothing resembling daylight. The landscape would exist in a permanent deep twilight. A world lit by a star that gives almost nothing away. This is the physical reality of a red dwarf. Small, cool, dim, and utterly unremarkable by any standard that astronomers once used to measure importance. Theoretical models built by Isabelle Barraf and Gilles Chabrier, whose work on low-mass stellar evolution has been foundational since the 1990s, describe objects that sit right at the edge of what it means to be a star at all. They are the minimum viable product of stellar physics, the least a collapsing cloud of gas can achieve and still ignite. But it is precisely this modesty that gives them their single extraordinary quality. Because a red dwarf burns so little fuel, so slowly, in a structure so different from anything larger, it lasts. Not for billions of years, but for trillions. Not for the lifespan of a sun, but for a span of time so vast that the human mind has no honest way to hold it. And the reason lies not just in how slowly they burn, but in how completely they use what they have. That mechanism, the engine of their immortality, begins deep inside the star, in a process that the sun itself cannot perform. Every star, regardless of its size, generates energy through the same fundamental reaction. Deep in the core, where temperatures reach millions of degrees and pressure crushes atoms into a state no earthly laboratories can sustain, hydrogen nuclei collide and fuse. The process is called the proton-proton chain, and it is the engine that powers every main sequence star in the universe. 4 hydrogen nuclei go in. 1 helium nucleus comes out. A small amount of mass is converted into energy along the way. Energy that works its way outward, eventually reaching the surface and escaping into space as light. In the Sun, this process runs fast. The core temperature exceeds 15 million Kelvin. The pressure is immense. Hydrogen nuclei slam into each other with enough force to overcome their natural electromagnetic repulsion, and the fusion rate is high enough to produce a luminosity visible from light years away. A red dwarf runs the same reaction. The physics is identical, but the conditions are not. A star with 1/10 the mass of the Sun does not simply produce 1/10 the energy. The relationship between mass and energy output is far steeper than that, scaling roughly with the 4th power of the star's mass. Halve the mass, and the luminosity does not halve. It can drop by a factor of more than 10. Reduce the mass to 1/10, and the output plummets to a 10,000th. The core of a low-mass red dwarf is cooler, less pressurized, and far less productive than the Sun's. Fusion still occurs, but it proceeds at a pace that would make the Sun look reckless. This alone would grant red dwarfs longer lives than larger stars. Less output means less fuel consumed per unit of time, which means a longer burn. But the real secret to their extraordinary longevity is not the rate at which they use fuel. It is how much of their fuel they can actually reach. Inside the Sun, energy generated in the core travels outward through 2 distinct zones. In the inner region, the radiative zone, photons carry the energy, bouncing endlessly between atoms in a slow, meandering journey toward the surface. Further out, in the convective zone, the energy is carried by physical motion. Great rising columns of hot plasma that deliver heat to the surface before cooling and sinking back down. The core and the convective zone do not mix. The hydrogen in the Sun's outer layers never reaches the core. It sits there, untouched, while only the hydrogen at the very centre is available for fusion. This amounts to roughly 10% of the Sun's total hydrogen supply. The remaining 90% will never be burned. When the core's fuel runs out, the Sun must restructure itself, swelling into a red giant, igniting hydrogen in a shell around the exhausted core, all because it cannot access what it already has. A red dwarf below approximately 0.35 solar masses faces none of this. Its interior is so dense, so opaque to radiation, that photons cannot efficiently carry energy outward at all. Convection takes over entirely. The star becomes fully convective, a single enormous circulation cell, stirring continuously from the core to the surface and back again. Hot material rises, cools, sinks, and is drawn back toward the centre, where it is heated once more. And crucially, it brings fresh hydrogen with it. This changes everything. A fully convective red dwarf does not burn 10% of its hydrogen. It burns nearly all of it. The entire star becomes fuel. No hydrogen is stranded. No reserves are left untouched. The star sips from its full supply, not merely from the small fraction trapped at the centre, and because it sips so slowly, the supply lasts for an almost incomprehensible length of time. The boundary where this transition occurs, around 0.35 solar masses, is not merely a theoretical landmark. It marks a genuine physical divide in the structure of stars. Above that mass, a red dwarf has a radiative core wrapped in a convective envelope, similar in architecture to the Sun. Below it, the entire star convex, and within that boundary lies a subtlety that would not be fully appreciated until decades after the first models were built. In the proton-proton chain, helium-3 is an intermediate product, a nucleus created part-way through the reaction sequence before being destroyed in the final step that produces helium-4. In the Sun's hot core, this destruction happens quickly, but in cooler red dwarfs sitting just above the convective boundary, the temperatures are not quite high enough to destroy helium-3 efficiently. It accumulates. Slowly over vast stretches of time, the concentration builds until the nuclei finally ignite in significant numbers, a delayed nuclear event that causes the star to brighten slightly and expand. This instability was predicted in 2012 by Jennifer Van Saders and Mark Pintono at Ohio State University, years before any observational evidence existed. It was a quiet, theoretical insight into the lives of quiet, theoretical stars. But it would not stay theoretical for long. Meanwhile, at the Lawrence Livermore National Laboratory, researchers have turned to the National Ignition Facility, the most powerful laser on Earth, to recreate the extreme pressures and relatively low temperatures found deep inside red dwarf interiors. Their goal is to measure the opacity of hydrogen under these conditions directly, because this single property determines whether a red dwarf's interior is dominated by radiation or convection. It determines, in other words, whether the star can access all of its fuel, or only a fraction. The answer to that question is the answer to how long these stars will live. And the answer, when the models are run, is staggering. A red dwarf with 1/10 the mass of the Sun has a calculated main sequence lifespan of approximately 10 trillion years. That number deserves a moment. The current age of the universe is 13.8 billion years. 10 trillion is roughly 700 times longer. If the entire history of the cosmos, from the first fraction of a second after the Big Bang through the formation of galaxies, the birth and death of generations of massive stars, the coalescence of the Earth, the emergence and evolution of life, and every moment of human civilization, were compressed into a single day, then 10 trillion years would stretch across nearly 2 full years. The relationship between mass and lifespan is not gentle. Stellar lifetimes scale by the third or fourth power of the mass ratio. A modest reduction in mass does not produce a modest increase in longevity. It produces an enormous one. A star half the mass of the Sun does not live twice as long. It lives many tens of times longer. A star at 1/10 of the Sun's mass lives not 10 times longer, but 1,000 times longer. The mathematics is unforgiving in its generosity to the small. Take Barnard's star, sitting 6 light-years from the Sun in the constellation Ophiuchus. It has a mass of approximately 0.16 solar masses. A small, dim, ancient-seeming red dwarf that was once briefly famous when an astronomer claimed to have detected planets around it in the 1960s, a claim that was later retracted. Barnard's star has a calculated main sequence lifespan of approximately 2.5 trillion years. It is currently estimated to be between 7 and 12 billion years old. That sounds ancient. In human terms, it is. In stellar terms, Barnard's star has completed less than half of 1% of its life. It is not middle-aged. It is not even young. It is, by any meaningful measure, a newborn. And this is the deepest strangeness of the red dwarf story. The universe is 13.8 billion years old, And in all that time, across every galaxy, every star-forming region, every corner of the observable cosmos, not a single red dwarf has progressed to an advanced stage of evolution. None has exhausted its fuel. None has left the main sequence. None has swelled, contracted, dimmed, or died. Every red dwarf that has ever existed is still on the main sequence right now, still in the opening chapter of a life that will continue for trillions of years after the last sun-like star has gone dark. Fred Adams and Greg Laughlin at the University of Michigan were among the first to fully calculate what this means. Their 1997 paper in the Astrophysical Journal, a landmark in stellar astrophysics, modelled the long-term evolution of red dwarfs for the first time, running simulations forward across timescales that no other stellar population requires. What they found was that these stars do not merely live longer than the Sun, they live in a fundamentally different relationship with time. The Sun is mortal in a way that can be imagined. 10 billion years is vast, but it is finite, and human beings have at least some instinct for what a beginning, middle, and end look like. A red dwarf exists on a timescale that defeats that instinct entirely. Its life is so long that the concept of age loses its ordinary meaning. If the Sun's lifespan were compressed into a single calendar year, a red dwarf at the bottom of the mass range would burn for a full millennium. 1,000 years of stellar life for every one of the suns. And we are standing right now in the first few hours of the first day of January, in a universe so young that the stars which will define its future have not yet had time to change. All of this, the mathematics, the models, the trillion-year timescales, can feel abstract. Numbers that large resist the imagination. But there is one red dwarf that is not abstract at all. It has a name, a measured distance, confirmed planets, and a position in the sky that makes it the closest star to our own Sun. Everything that defines the red dwarf story, the patience, the dimness, the hidden violence, the staggering longevity, is embodied in a single object sitting just 4.25 light-years away in the constellation Centaurus. Proxima Centauri, the nearest star, and you have never seen it. It has a mass of roughly 0.12 times that of the Sun, small even by red dwarf standards. Its surface temperature hovers around 3040 Kelvin, cool enough to glow a deep, sullen red. Its total luminosity is approximately 0.17% of the Sun's. If you replace the Sun with Proxima Centauri tomorrow, the Earth would receive so little light that the oceans would freeze solid within years. This is not a star that announces itself. It is a star you have to go looking for. And yet it is ancient. Estimates place Proxima Centauri's age at roughly 4.85 billion years, almost exactly the age of our own solar system. It has been burning for as long as the Sun has, through the same eras of cosmic history, watching the same galaxy evolve around it. But where the Sun is now approaching the midpoint of its life, Proxima Centauri has barely started. It will remain on the main sequence for another 4 trillion years. The time it has already lived represents less than 1/5 of 1% of its total lifespan. In human terms, it is an infant taking its first breath in a life that will stretch across centuries. Its interior churns continuously. Because its mass falls well below the 0.35 solar mass boundary, Proxima Centauri is fully convective. Hydrogen from the outermost layers is drawn inward, fused in the core, and the products are carried back to the surface in an endless cycle of mixing. It will burn through nearly all of its hydrogen supply before it is done. No fuel wasted, no reserves unreachable. Its magnetic field is generated by this same convection. The churning motion of electrically charged plasma creating a dynamo that threads the entire star with magnetic energy. Approximately 88% of Proxima Centauri's surface is magnetically active at any given time. That is an extraordinary figure. Even at the peak of the Sun's 11-year activity cycle, only a fraction of its surface shows comparable levels of magnetic disturbance. Proxima Centauri, despite its modest size, produces total X-ray emissions comparable to the Sun's. It punches far above its weight in the violence of its magnetic behaviour. This violence became personal in 2016. That year, a team of astronomers confirmed the existence of Proxima Centauri b, a planet with a minimum mass of roughly 1.06 times that of Earth, orbiting within the star's habitable zone. The discovery electrified the field. The nearest star to the Sun had an Earth mass world in the region where liquid water could theoretically exist on its surface. It was the closest potentially habitable planet ever found, and it orbited a red dwarf, the most common type of star in the galaxy. If this one star could host such a world, the implications for the abundance of temperate planets across the Milky Way were staggering. But there was a complication. There is always a complication with red dwarfs. Proxima Centauri is a flare star. It does not burn steadily. Beneath that churning, magnetically tortured surface, energy builds in twisted loops of magnetic field until the tension becomes unsustainable, and the field reconnects in a violent release. The result is a stellar flare, a sudden, explosive burst of radiation across the electromagnetic spectrum, from radio waves through visible light to ultraviolet and X-rays. Flares on the Sun are significant events. Flares on red dwarfs can be catastrophic. In 2019, Proxima Centauri produced the most powerful stellar flare ever recorded from a red dwarf. For a few seconds, the star's brightness surged to 14,000 times its quiescent luminosity. 14,000 times? A star that is ordinarily invisible to the naked eye momentarily blazed with a ferocity that would have been visible across interstellar distances. The flare was detected across multiple wavelengths, including millimetre wave observations by the Atacama Large Millimetre Array in Chile. Work later expanded by Kiana Burton at the University of Colorado, whose studies of Proxima Centauri's millimetre flare rate revealed that energetic outbursts at those wavelengths are far more frequent than optical flares alone would suggest. The implication was troubling. If you only watched in visible light, you were underestimating the radiation environment around this star. The storm was worse than it looked. This is not unique to Proxima Centauri. Red dwarfs across the mass range exhibit flare behaviour. Star spots, dark, magnetically suppressed regions on the surface, can cover up to 40% of a red dwarf's visible disk, reducing its output for weeks or months at a time before the star erupts in violent flaring. The first astronomers to document this behaviour were Einar Hertzsprung and Adrian van Maanen, who identified sudden brightness increases in certain nearby red dwarfs during the 1920s and 30s. The prototype became a star called ultraviolet Ceti, and for decades the phenomenon was treated as a curiosity, an interesting footnote in the lives of otherwise unremarkable stars. It is no longer a footnote. The violent flaring period of a young red dwarf was once estimated to last roughly 1 to 2 billion years, a turbulent adolescence after which the star would settle into a calmer maturity. But observations have challenged that assumption. Barnard's star, estimated to be between 7 and 12 billion years old, and long considered one of the quieter red dwarfs, produced a significant flare in 1998. If a star that ancient could still erupt, the window of danger was far wider than models had predicted. More recently, in 2025, a study led by Lucille Mignon at the University Grenoble Alps examined 177 M dwarfs over extended timescales to characterise their long-term variability. The conclusion sharpened the problem further. Even the calmest red dwarfs in the sample, the ones with the least dramatic short-term behaviour, exhibited more long-term variability than the Sun. There appears to be no such thing as a truly quiet red dwarf. The magnetic activity may diminish with age, but it does not vanish. These stars carry their volatility with them across billions of years. The paradox is now fully visible. The longest-lived stars in the universe, the ones that will still be burning trillions of years from now, long after every other stellar light has gone out, are also among the most temperamental. They endure, but they do not endure gently. A planet in orbit around one of these stars would need to survive not just the initial fury of its host's youth, but an ongoing low-level bombardment that persists across timescales no other type of star requires. The question of whether anything can live beside a red dwarf is not a question about a brief window of danger. It is a question about eternity. And that question, it turns out, has been given its most dramatic testing ground not around Proxima Centauri, but around another red dwarf, one slightly further away, slightly cooler, and home to not one potentially habitable world, but 3. In February of 2017, NASA announced something remarkable. A star called TRAPPIST-1, an ultra-cool red dwarf roughly 40 light-years from Earth in the constellation Aquarius, had been found to host not 1, not 2, but 7 Earth-sized planets. All 7 were detected through the transit method, meaning each one periodically crosses the face of its star as seen from our vantage point, dimming the light by a tiny, measurable amount. That geometry gave astronomers something rare and precious: mass and radius estimates for every planet in the system. 3 of them, TRAPPIST-1a, F, and G, orbit within the star's habitable zone, the region where surface temperatures could, in principle, permit liquid water. The discovery was led by Michael Gillen at the University of Liège in Belgium, and it changed the conversation about red dwarfs overnight. Here was a system that seemed almost designed for study. The star is small, just 9% of the Sun's mass, barely above the boundary separating red dwarfs from brown dwarfs. Its planets orbit extraordinarily close, completing full orbits in as little as 1.5 Earth days for the innermost world and up to roughly 19 days for the outermost. The habitable zone of a star this faint is drawn tight against it, so close that a habitable zone planet's year lasts less than 3 Earth weeks. The system is astonishingly compact. All 7 planets orbit closer to TRAPPIST-1 than Mercury orbits the Sun. From the surface of any one of them, the others would be visible to the naked eye, not as points of light, but as disks, some appearing larger than the full moon does from Earth. It is a solar system built on a miniature scale, packed into a space so small that the outermost planet sits closer to its star than Mercury does to ours. This compactness is not accidental. Observations of young red dwarfs have revealed that their protoplanetary disks, the swirling rings of gas and dust from which planets form, can persist for far longer than those around more massive stars. Some, nicknamed Peter Pan disks, have been found surviving up to 45 million years, several times longer than typical. This extended lifespan may allow the slow, methodical construction of tightly packed planetary systems held in gravitational resonance. each planet's orbit locked into a precise mathematical relationship with its neighbours. TRAPPIST-1's planets are exactly this kind of system. A chain of resonances so orderly it almost resembles clockwork. The implications for habitability were tantalising. 40% of red dwarfs are estimated to host at least one super-Earth-class planet in the habitable zone. Given that red dwarfs account for 3/4 of all stars, that figure translates into billions of potentially temperate worlds in the Milky Way alone. If even a small fraction of those worlds could sustain liquid water, or life, then the universe is a far more populated place than our own solar system suggests. But the James Webb Space Telescope delivered a sobering correction. Observations of TRAPPIST-1b and c, the two innermost planets, both orbiting outside the habitable zone, found no detectable atmospheres. These worlds appear to be bare rock, their surfaces exposed directly to the vacuum of space. The most likely explanation is that the star's intense radiation, particularly during its violent early years, stripped whatever atmospheres these planets once possessed. Whether the outer worlds, deeper in the habitable zone, have fared better remains an open question. But the inner planets stand as a warning. Proximity to a red dwarf is a bargain with terms attached. The habitability paradox sharpens here into something uncomfortable. If red dwarfs truly cannot sustain atmospheres on nearby planets, if their flaring and radiation strip the air from every world close enough to receive warmth, then roughly 75% of all stellar systems in the galaxy are lifeless by default. 3/4 of the stars in the Milky Way hosting worlds that are temperate in theory and barren in practice. That is a profound constraint on where life can exist, and it remains one of the most actively debated questions in modern astrophysics. The answer, when it comes, will depend in part on how well we understand the stars themselves. And on that front, a discovery made in 2018 revealed that the most common stars in the cosmos had been keeping a secret, one hidden not in their surfaces or their planets, but deep inside their structure. Wei-Chun Zhao was not looking for a gap. He was examining data from the European Space Agency's Gaia spacecraft, a mission that had catalogued the positions, distances, and brightnesses of over 1 billion stars with unprecedented precision. Gaia's second data release, in April of 2018, was a watershed moment for stellar astronomy. For the first time, the Hertzsprung-Russell diagram, the foundational chart that plots a star's luminosity against its temperature, revealing its mass, its size, and its stage of evolution, could be drawn with a level of detail that previous generations of astronomers could not have imagined. Zhao, working at Georgia State University alongside his colleague Todd Henry, was studying the faint, cool end of the main sequence, the region populated by red dwarfs. And there, running diagonally through the data, was something no one had seen before. A narrow but unmistakable gap. A thin band of luminosities where red dwarfs were conspicuously scarce, not absent, but far less numerous than the stars immediately brighter or fainter. The gap was subtle. It spanned only about 0.05 magnitudes, but it was real, confirmed independently in infrared data from the 2-mass survey, and it fell precisely at the mass where red dwarfs are thought to transition from partially convective to fully convective interiors, around 0.35 solar masses near spectral type M3. Zhao had found a visible fingerprint of a star's invisible interior. The significance was immediate. 6 years earlier, Jennifer Van Saders, then a second-year graduate student at Ohio State, working under the supervision of Marc Pinsonneau, had published a paper predicting that red dwarfs near the convective boundary should undergo slow, periodic pulsations. The mechanism was the helium-3 instability described earlier. In stars just above the mass, where full convection begins, helium-3 accumulates in the core until it ignites, causing the star to brighten slightly, expand, and then contract as the excess helium-3 is mixed away. This cycle repeats over long timescales, and critically, it causes stars to spend less time at a particular luminosity, creating exactly the kind of gap Joule had discovered. Van Solders and Pinsonneau had predicted the phenomenon before Gaia had even launched. When the data arrived, the match was striking. Shortly after Joule's paper appeared, James McDonald and John Gizis at the University of Delaware published an independent theoretical explanation, arriving at a consistent picture through standard stellar evolution models. The gap was not an anomaly. It was a feature, a natural consequence of the physics occurring inside these stars at the precise mass where their internal structure changes. Pavel Krupa, an astronomer at the University of Bonn and a leading expert on how frequently stars are born at different masses, called the discovery a beautiful advance. He noted that the gap functions as an extraordinarily sensitive diagnostic, a tool for testing models of stellar interiors with a precision that was previously impossible. If any element of the physics is even slightly wrong, the nuclear reaction rates, the treatment of convection, the chemical composition, the predicted location of the gap shifts. It is, in Van Sader's words, a signpost, a direct, observable marker of what is happening in the deep interior of the most common stars in the universe. The Joule gap did something else too. It reminded astronomers that red dwarfs, for all their apparent simplicity, are not fully understood. These are objects that have been burning without interruption since long before the Earth existed, and yet the physics of their interiors, the precise interplay of opacity, convection, magnetic fields, and nuclear reactions, still hold uncertainties that decades of modelling have not resolved. The stars that make up 3/4 of the galaxy are, in a very real sense, still being discovered. And the tools to discover them, spacecraft like Gaia, facilities like the National Ignition Facility, theoretical frameworks refined by generations of astrophysicists, are only now reaching the sensitivity required to ask the right questions. What those questions reveal, when the models are extended forward across trillions of years, is a future that no human being will ever witness, and a mystery that reaches all the way back to the beginning of the universe itself. The universe began with almost nothing. Hydrogen, helium, and trace amounts of lithium, forged in the first few minutes after the Big Bang, before the cosmos had cooled enough for anything more complex to survive. No carbon, no oxygen, no iron, no silicon. Nothing heavier than the third element on the periodic table. The first stars had to be built from this alone. Astrophysicists call that primordial generation population 3, the oldest, most metal-poor stars theoretically possible. In the language of astronomy, a metal is any element heavier than helium, and population 3 stars would have contained none. They would have formed from pristine clouds of hydrogen and helium, collapsing under gravity in a universe that had not yet been enriched by the deaths of earlier stars, because there were no earlier stars. They were the first. The prevailing models predict that these first stars were giants. Without heavier elements to help cool the collapsing gas clouds efficiently, the fragments that formed were large, perhaps tens or even hundreds of times the mass of the Sun. stars that massive burn through their fuel in a few million years and die violently, scattering the heavier elements they forged in their cores across the surrounding space in supernova explosions. Those elements, the metals, seeded the next generation of gas clouds, enriching them just enough to allow smaller, cooler, less massive stars to form. Red dwarfs in this picture are a product of that enrichment. They could not exist until the universe had been seasoned by the deaths of the first giants. But here is the puzzle. If any red dwarfs did manage to form in that primordial environment, if the conditions were not quite as hostile to low-mass star formation as the models suggest, those stars should still be alive today. A red dwarf with a lifespan of trillions of years, born 13 billion years ago, would have consumed a negligible fraction of its fuel. It would still be sitting on the main sequence, burning quietly, carrying a chemical fingerprint unlike any other star in the sky. A complete absence of metals, pure hydrogen and helium, and nothing else. No such star has ever been found. Every red dwarf ever observed contains metals. Even the most ancient, most metal-poor red dwarfs in the galaxy carry traces of heavier elements. Proof that they formed from material that had already been processed through at least one generation of massive stars. The primordial red dwarf, the metal-free survivor from the dawn of time, does not appear to exist. This is not for lack of searching. As detection methods have improved, as surveys have pushed deeper into the galaxy, and instruments have grown more sensitive to the faintest, coolest stars, the scarcity has been confirmed rather than resolved. Improved observations have found fewer metal-poor red dwarfs than even pessimistic models predicted. The mystery has deepened, not dissipated. The most widely accepted explanation remains the simplest. The conditions of the early universe genuinely prevented low-mass stars from forming. Without metals to aid in cooling, primordial gas clouds could not fragment into pieces small enough to become red dwarfs. Only massive stars formed, and only after those massive stars died and enriched their surroundings could the smaller, longer-lived stars appear. Red dwarfs, in this view, are latecomers, born not in the first act of the cosmic story, but in the second, after the stage had been set by a generation of stars they will never meet. It is a satisfying answer, but not a complete one. The precise physics of primordial star formation remains an area of active research, and the total absence of metal-free red dwarfs is a constraint that any successful model must explain. It connects the smallest, most patient stars in the universe directly to its most violent and ancient events. The first supernovae, the first chemical enrichment, the transition from a cosmos of pure simplicity to one capable of producing complexity. Every red dwarf burning today carries within it the legacy of a star that died before it was born. And every red dwarf burning today will eventually die too. Not soon, not for trillions of years. But the models do predict an ending, and it is unlike the death of any star the universe has yet produced. When a red dwarf below approximately 0.25 solar masses finally exhausts its hydrogen, after burning for timescales that dwarf the current age of the cosmos, it faces a problem that every aging star must solve. As the fuel runs low, the internal physics shifts. The star needs to radiate more energy to maintain equilibrium, and it must find a way to do so. For a star like the Sun, the solution is expansion. The outer layers swell outward, the surface cools, and the star becomes a red giant, hundreds of times its original size, bright enough to swallow the inner planets of its solar system. This is the path that awaits the Sun in roughly 5 billion years. It is dramatic, destructive, and comparatively brief. A low-mass red dwarf cannot take that path. It lacks the mass to ignite helium fusion in its core, which is the process that drives red giant expansion in heavier stars. Without that secondary energy source, the star cannot inflate. It is stuck, in a sense. Too small to grow, but still needing to shed the increasing energy produced by its contracting core. The solution it finds is the opposite of what the Sun will do. Instead of growing larger and cooler, the red dwarf grows hotter while remaining small. Its atmosphere, unlike the opaque outer layers of a more massive star, is relatively transparent. It can radiate more energy simply by increasing its surface temperature, letting more light escape per unit of surface area without needing to increase that area at all. The star does not expand outwards, it heats up. This produces something that exists nowhere in the observable universe: a blue dwarf, a compact, increasingly hot star, transitioning from red through yellow to white to blue as its surface temperature climbs. The name is somewhat misleading because not all of these objects would become visually blue. The hottest examples in the simulations, originating from red dwarfs of around 0.14 solar masses, reach surface temperatures of approximately 8,600 Kelvin, hot enough to appear distinctly blue-white, comparable in colour to a star like Vega. Others would reach only yellow or white before their fuel was fully spent. The foundational work on this phase belongs to Greg Laughlin, Peter Bodenheimer, and Fred Adams, whose 1997 paper in the Astrophysical Journal first modelled the complete evolutionary trajectory of red dwarfs from birth through the main sequence, through the blue dwarf phase, and into their final state. For a star like Barnard's star, at 0.16 solar masses, the models predict 2.5 trillion years on the main sequence, followed by roughly 5 billion years as a blue dwarf, a brief, comparatively bright coda to an almost inconceivably long life. During that phase, the star would reach approximately 1/3 of the Sun's current luminosity and a surface temperature between 6,500 and 8,500 Kelvin. For a few billion years, a star that spent trillions of years as a dim red ember would shine with a light not unlike our own suns. And then it would stop. With its hydrogen fully spent and no heavier fuel to ignite, the blue dwarf would contract and cool, becoming a helium-white dwarf, a dense, inert remnant radiating away its stored heat into an increasingly cold universe. Over further billions of years, even that faint glow would fade, and the star would become what theorists call a black dwarf, an object so cold it emits no detectable radiation at all, a stellar corpse, dark and silent, drifting through a universe that has long since moved beyond the age of stars. None of this has happened yet. The universe is far too young. No red dwarf has reached the blue dwarf phase. No blue dwarf exists. No helium-white dwarf produced by this pathway has ever formed. The entire final act of the red dwarf story is a prediction, a projection built from physics and mathematics, extrapolated across timescales so vast that the word future barely applies. We are modelling the deaths of stars that will not die for an interval of time that exceeds everything that has ever happened in all of cosmic history by a factor of hundreds. And yet, the models are not speculation. They are grounded in the same physics that accurately describes the stars we can observe. The same nuclear reaction rates, the same convective processes, the same opacity calculations that are being tested right now in facilities like the National Ignition Facility. The physics is real, only the timescale is beyond us. What remains then is to follow that timescale to its conclusion, to ask what the universe looks like when the red dwarfs are not merely the most common stars, but the only stars burning alone in a cosmos that has otherwise gone dark. Fred Adams and Greg Laughlin saw further than most. In their 1999 book, The 5 Ages of the Universe, they divided the entire lifespan of the cosmos into 5 distinct eras, not based on human history or geological time, but on the physics that dominates each epoch. The primordial era covers the first few million years, the Big Bang, the cooling plasma, the formation of the lightest elements. The stelliferous era, the age of stars, begins when the first hydrogen clouds collapse and ignite, and it is the era we inhabit now. After it comes the degenerate era, when the last stars have faded, and the universe is populated only by their remnants: white dwarfs, neutron stars, brown dwarfs, and black holes. Then the black hole era, when even those remnants have decayed and only black holes persist, slowly evaporating through Hawking radiation across timescales that make 1 trillion years feel like a heartbeat. And finally, the dark era, a universe with no structure, no energy sources, no light, just elementary particles drifting through an expanding void with no meaningful events left to occur. We live in the stelliferous era. It is in many ways the only era that matters to us. The window in which stars shine, planets form, chemistry complexifies, and life becomes possible. Every civilization that has ever existed or ever will exist in anything resembling our form belongs to this single chapter of the cosmic story. And it is the red dwarfs that will write its final pages. The sequence is not hard to follow. The most massive stars, blue supergiants, the brief and brilliant ones, are already dying, have been dying for billions of years. They live fast, burn through their hydrogen in a few million years, and collapse or explode. The next tier, the sun-like stars, last longer, billions of years. But they too will eventually exhaust their fuel, swell into red giants, and shed their outer layers, leaving behind white dwarfs. One by one, class by class, the brighter stars will go dark. And as they do, the galaxy will dim. Not suddenly, not dramatically. Slowly, over timescales that stretch far beyond the current age of the cosmos. Genevieve Graves and Greg Laughlin modelled this decline in 2003. They calculated the projected light curve of the Milky Way, the total luminosity of the galaxy plotted forward over the next 10 trillion years. What the model shows is a long, patient descent. As sun-like stars age and die, and are not replaced because the raw material for new star formation is gradually used up, the galaxy's total brightness falls. The blue and white light of hot stars fades first, then the yellow light of stars like ours, and eventually the only contribution left comes from the red dwarfs, dim, cool, and still burning. The Milky Way in this projection does not go dark all at once. It goes red, then dimmer still. The light curve flattens into a long, low tail that stretches across trillions of years, sustained entirely by the smallest, slowest stars in existence. The stelliferous era ends, in Adams and Laughlin's framework, approximately 100 trillion years from now. That is the point at which the last red dwarf, the very lowest mass, the most miserly with its fuel, finally exhausts its hydrogen, passes through the blue dwarf phase, and cools into a helium-white dwarf. After that, no conventional star burns anywhere. The universe enters the degenerate era. It is not entirely dark. Occasionally, once every quadrillion years or so, in a galaxy the size of the Milky Way, 2 brown dwarfs will drift close enough to merge, and the combined mass will be just sufficient to ignite hydrogen fusion. A new star will flicker into existence, small and faint, burning for trillions of years before it too goes out. These are candles lit by accident in an otherwise empty cathedral. They are real in the models, but they are rare beyond any human sense of the word. The age of starlight, as a defining feature of the universe, is over. What comes after belongs to a different kind of physics entirely. Proton decay, black hole evaporation, the slow unwinding of matter itself across timescales so vast they can only be written in powers of 10. That story is beyond the scope of what red dwarfs can tell us. But the red dwarfs are the bridge. They are the last objects to carry the torch of nuclear fusion, the process that has powered every star, warmed every planet, and driven every act of chemistry that has ever led to life. When the red dwarfs stop burning, that chain is broken. Not paused. Broken. The universe moves on, but it moves on without light. There is something worth sitting with in all of this. Not the ending, the beginning. Because the most remarkable thing about red dwarfs is not that they will be the last stars to die, it is that they have barely started living. Every red dwarf currently burning in the Milky Way was already there when the first galaxies assembled themselves from collapsing filaments of dark matter. They were burning when the first heavy elements, the carbon, the oxygen, the iron that would one day become the Earth, were forged in the cores of massive stars and scattered into space by supernovae. They were burning when the solar nebula condensed, when the sun ignited, when the oceans filled, when the first single-celled organisms divided in warm water on a young planet. They have been burning through every moment of cosmic history that has ever mattered to us, and they will still be burning long after every trace of us is gone. The sun will swell and consume the inner solar system in roughly 5 billion years. It will shed its outer layers and collapse into a white dwarf, cooling slowly over the aeons. The Milky Way will merge with Andromeda in approximately 4.5 billion years, reshaping both galaxies into a single vast elliptical structure. New stars will form from the collision for a time, but eventually the gas will be spent. The last sun-like stars will fade. The sky, if anything remained to look at it, would grow darker with each passing epoch. And through all of it, the red dwarfs will still be there. Proxima Centauri, Barnard's Star, Wolf 359, Ross 128, and billions more with no name at all scattered through every corner of the galaxy, burning so faintly that no instrument we currently possess could detect them at interstellar distances. They will not notice the sun's death. They will not be affected by the galactic merger. They are too small and too cool for any of those events to matter. They simply continue, patiently, quietly, for trillions of years. We exist in the first fraction of 1% of the stelliferous era. The universe is 13.8 billion years old. The era of stars will last 100 trillion years. We are not at the midpoint. We're not even close. We are at the very beginning, a thin sliver of time so early in the story that the defining stars of the cosmos have not yet had time to change. The red dwarfs that surround us are, in every meaningful sense, newborns. They carry nearly all of the hydrogen they were born with. They have not brightened, not evolved, not aged in any measurable way. They are today almost exactly what they were the moment they ignited, and they will remain so for an interval of time that dwarfs everything that has happened before. There is a kind of quiet grace in that, A star too small to see, too cool to warm a planet from any comfortable distance, too dim to earn a name in any catalogue, burning steadily in the dark, asking nothing, needing nothing, outlasting everything. Not because it is powerful, because it is patient. Because the universe, it turns out, does not reward the brightest or the most spectacular. It rewards the slow, the efficient, the unnoticed. The stars too small to die are not a footnote in the story of the cosmos. They are the story. The rest, the supernovae, the black holes, the blazing blue giants, are the prologue. The real narrative, the one that stretches from now until the last fusion reaction in the last red dwarf in the last galaxy has only just begun. And it will be written in a light so faint that no human eye will ever see it. But it will burn longer than anything else the universe has ever made.